Hello, good afternoon. Thank you for coming to the next session. I'm very excited to be here in London. My name is Peter Moskovits, and the topic that we are going to talk about today is basically a journey that shows you and shows all of us how we can take some very awesome web communications technologies and stretch them to the absolute limits, and how we can eventually arrive to the quadcopter that's sitting out here, and how we can ideally get some very neat real-time information off of that copter. I work for a company called Kaazing. Kaazing is in Silicon Valley. We have about 65 employees, and I've been at Kaazing for about 3 years. And Kaazing has a real-time web communications platform, a very secure, very low latency, and very scalable WebSocket platform. Kaazing was one of the main contributors to the WebSocket standard. We authored a very significant chunk of the standard. So, to get started on this journey, I wanted to show you a handful of demonstrations, just to set the stage. Let's get started with this one and see if the demo gods are with us. I have my iPad here with me, and on the screen you see in the browser a canvas tag, and a ball is bouncing around on the screen. And you see on my iPad kind of a similar canvas tag in a browser, and the ball is bouncing around. And now I'm attempting to connect the two screens, and the ball is bouncing across the boundaries of these two screens. As the ball reaches the common edge of the browser, it bounces over from one to the other. So this is one very quick example. This is one of the first demos that I built when I joined Kaazing. The next one I wanted to show you is a trading platform application. Here you see about 100 messages coming in per second. On the left-hand side, I have foreign exchange currency pairs that I can drop on the dashboard, and as I'm dropping them on here, I see this, all this data change as it is coming from a simulated backend. The server where the data is coming from is sitting in the US on the East Coast. Okay, let's take a look at a next one. This is going to be a live one as well. Here you see a race car rendered in the browser, where that is rendered using WebGL. And I can use my keyboard to drive this car around. You can see the neat reflections. It's all pretty cool. And now I'm going to take the browser on my phone, and I will connect here. And as I connect, I start tilting my phone. And as I am tilting my phone, I'm driving the car around. So what's happening here is that there is a JavaScript API that's running on my phone that allows me to detect the tilt status. And as all these tilt events are happening, I am publishing some messages out there to the web, and this guy here is listening to all these messages. So later on we are going to review what the architecture and what the technology is behind all these demos. One thing to keep in mind is that unlike in a more traditional web application, there is no page rendering on the server side and markup rendering on the server side. There is a page loaded here that is receiving live data and inputs coming in here. Okay, let me show another one. This one is used to be my favorite for a long time. On the left-hand side, you see my laptop screen, and I'm leaning my iPad against that screen. I have a browser open with a number of images on there, and on the iPad I open the exact same page. And then I start interacting with these images. I am resizing, moving the images around, and you can see these interactions are reflected on the other screen with this in a very low latency fashion. So I'm moving them around. You can imagine that this is a neat scenario for when you want to show some images to your friend or your mom. You can do that very easily. So now I'm going to prepare and move 2 images at the same time. On a touch surface, it's very easy. On a laptop, it wouldn't be that straightforward. Okay, now I'm moving over to the laptop side, and I start interacting there, and notice that the interactions are mirrored over on the iPad side. Here is the second image. And as I am doing this, I'm getting ready for the kind of peak of the magic trick. With one hand, I'm interacting on the laptop, the flower, and with my other hand, I'm interacting on the iPad. So you see there is this bidirectional, very low latency communication between the 2 worlds, very much like in a Google Doc editing scenario where I am editing one paragraph, you are editing the other paragraph, and we see each other's edits. Okay, there was a last one I wanted to show. And this is more from the media entertainment space. On the left-hand side is a TV. On the right-hand side is a mobile device. And I'm connecting to the experience. Let's say this is a live sport event, happens to be baseball. And as the events are unfolding on the big screen TV, very often we find ourselves Googling and Facebooking and tweeting. And what an experience, a second screen kind of experience like this, entails is that you get some questions on your mobile device, and then you can wager, you can bet a certain amount of toy money, and then you can submit your vote on the mobile device. And you can see that eventually the big event, the pitch is going to happen. And here we are betting whether it's going to be a ball or a strike, what part of that little rectangle the ball is going to go. It turned out to be a ball. Notice that on the big screen as well as on the mobile screen, ball is flashing, indicating what has happened. And the leaderboard has been updated as well. Our name was ACOS, and our score got updated. So it shows how you can leverage this very low latency real-time communication in various different spaces. This is a scenario where obviously a bunch of different clients would connect and they are playing along, and they are affecting or they are influencing what is shown on the big screen, and the big screen is kind of playing along. Okay? So I wanted to show these examples so that we have a kind of a appreciation for what we are going to talk about. So what is this technology that allows and supports all of this? My assumption is that many, if not all of you, are familiar or heard of at least the HTML5 WebSocket standard. This is a standard that has been out there for over 2 years now, was ratified in 2011 December, and the WebSocket standard has a dual nature. Interestingly, it's both a wire protocol. It defines what bits and bytes are traveling on the wire, and it's also an API. The API was defined originally for JavaScript, but there are more and more languages that are supporting it. The first standard, the protocol, is controlled by IETF. The language is controlled by W3C. And the real power of WebSocket is that unlike HTTP, where we have a request-response kind of world, in the WebSocket world we have a permanent connection between the client, which is very often a web browser, and the server. Very much like in the world of HTTP, you need to have a server for WebSocket connections over on the server side, and Kaazing happens to be such a server, but there are many, many open source servers, and many application servers are starting to support it as well. The beauty of WebSocket is that the overhead is very, very small compared to HTTP. When you are sending an HTTP request, the header size can be 800 to 1600 bytes. Anywhere there in that range for WebSocket, that can be 4 to 8 bytes. It's very, very small. So especially when you have a lot of data going back and forth, it can be very efficient. And just like HTTP, there is a TLS tunneling support, SSL support for WebSocket as well. WebSocket, the first 3 letters of WebSocket is basically the key contribution of Kaazing. WebSocket indicating that it's a web-friendly socket connection. In the old world, when we had Applet and Flash running in the browser, we had TCP connection to the back end, and that had all sorts of challenges and issues, mainly that we had to open ports on firewalls. It was just not a web-friendly kind of communication. WebSocket supports the same ports as HTTP, port 80 and port 443. So in the world of the legacy web, the web that we live mainly today, we have a full duplex connection between our back-end server and our middleware. However, between our browser and our middleware, we have a half duplex connection. So typically the life cycle of a request is I'm clicking on a link or entering a URL. The server does a call to the backend. The backend returns some data. Some rendering is happening on the middle tier. And the browser is used as a dumb rendering device. In the WebSocket world, we do have a full duplex connection all the way from the browser or mobile device to the WebSocket server, and from the WebSocket server, we have a full duplex connection to the back end. Now, this has very serious implications. The serious implications are that now we can build truly event-driven applications. We can build applications where it's not only the browser that can initiate connections to the middle tier, but anywhere in the back end, events happening can be populated and sent out all the way to the browser or all the way to the mobile device. There's another very important and interesting implication. In the world of application servers, the actual application tends to run on the middle tier, on the application server tier. And that means that as your user population is growing, that's something that you need to scale out. In this new world, and especially by taking advantage of all the evolution in the runtime execution of JavaScript, now we have the ability to run a lot of the application logic actually on the client. That means that we can use HTTP to get the HTML, CSS, JavaScript code onto the client, and then the client code can execute. And from that point on, it can have a bidirectional communication all the way to the back end. There is no re-rendering of the page. There is no execution on the server side other than getting the data, the dynamic data, into the browser. So just think about the car that I was driving around. What was happening was initially the assets got downloaded into the browser, and then the tilt information that I have here on my phone, some magical way, managed to get to the browser and to the code that actually rendered the car in the browser. So let's talk a little bit about how you are building applications. Basically, when we were forced to use HTTP, we always wanted to build very rich and very responsive apps. And therefore, we came up with very clever and very smart solutions, things like polling and long polling and Comet technologies and various forms of AJAX. But now with WebSocket, we have finally the right tools to build these kinds of very rich applications. When you think of the TCP world, let's say you are building a thick chat application, or you're building an email application, you would barely ever go down to the TCP level. You would use some higher level protocols. You would use Jabber or XMPP for chat. You would use IMAP or SMTP or POP3 for email, right? So if we have WebSocket that is basically, has the same power as TCP has, but now we have it in the world of the web, what would stop us from building higher level, richer business protocols on top of this WebSocket layer? And if we decide to do so, that means we can build very similar kinds of applications that what we've been used to in the good old client-server world. Basically, we have a client where we do not have the maintenance nightmare of the code, simply because the client code is downloaded over HTTP into the browser. And then we have a full duplex connection that goes all the way to the back end that allows us to have the same level of richness than what we had in the world of TCP thick client application world. So examples for these higher level protocols could be AMQP or MQTT. These are messaging protocols, PubSub protocols on top of a WebSocket. Here is a slightly different angle of the same story, where we have TCP. On top of TCP runs WebSocket, just like HTTP as we saw in the previous one. And then we can build higher level, richer protocols and APIs on top of this. And on top of it are sitting our applications. Okay, so if we have a WebSocket server, then the clients are connecting to it. As I mentioned, just like for HTTP, you need an HTTP server. For WebSocket, you need a WebSocket server. These clients are most frequently web browsers, but they can be other clients as well. There are WebSocket libraries for Java, for Python, for other languages as well. But since we have all this WebSocket connection out there to the clients, now we have the ability to take our highly rich and very much event-driven enterprise applications and extend them all the way to the web. So if you have a message bus, message broker that connects your various backend systems, now it's very straightforward and very easy to build the same kinds of protocols, the same kinds of APIs on top of that, and extend that functionality all the way to the browsers. So if you just think of the foreign exchange demo that I showed in the beginning of the presentation, we have some trading feed. That trading feed publishes the data to the message broker, and traditionally all these trading feeds were accessible through clients within the enterprise network. But now you can take all of this and extend it in a very seamless and very straightforward fashion to browsers and to mobile devices without actually the message broker or the message bus even being aware that those are clients running on the client. So many of our customers are using this technology exactly in this fashion. Okay, so this is kind of the high-level web and software-only scenario. But I think where this becomes really interesting is when we can take actual physical devices and we can use this technology to kind of bridge the gap between software and hardware. So what we did in one of our little experiments is we got a Raspberry Pi. If you're not familiar with the Raspberry Pi, it's a credit card-sized little computer that can run Linux on it. It has 2 USB ports, 1 or 2 depending on the edition that you are getting. It has an Ethernet port. It has HDMI. You can power it through USB. It has audio and video ports. It has an SD card that can be used as its storage. So this is where the OS would go. In our case, it would be Linux. And most importantly, it has these general-purpose input-output ports. These general-purpose input-output ports allow us to detect various inputs coming from the outside and create outputs using software. So this is the magic that is happening when you are bridging the world of software and hardware. So our first experiment is probably as basic as it gets. We have a switch and we have a light. What does the switch do? It allows you to toggle. And when you toggle the switch, then there is a way to detect that on the Raspberry Pi. What does the light do? Well, the light can be on or off. So the Raspberry Pi allows us to execute some software and turn the light on and off or control it using these general-purpose input-output ports. So if we can do that, then we can either directly connect these two, or how about, given that the Raspberry Pi is pretty much a full-blown computer, we use the same kind of publish, subscribe kind of trick that we saw in the previous slide. And instead of directly connecting the two, we couple them in a loose fashion. So whenever the switch is toggled, a piece of information, it's detected by the Pi, it's sent over the web to a back-end system. In our case, the simplest one would be probably a message broker. And this message broker, it has all the routing information about the message that came in and said that, hey, anybody out there interested about the switch being toggled? And then here is this guy who is interested in the toggle state. So the information comes in, the message comes into the Raspberry Pi. The Raspberry Pi puts the right signal onto the input-output port, and it turns the light on or off. And given that we are using the web to get all this communication across, now we can do something really interesting. You can have the switch on one continent and the light on another continent, and the only thing that would need to be present in at both ends is web connectivity. So if you have the Pi on the left-hand side connected to the web and the Pi on the right-hand side connected to the web, then this guy publishing the toggle information would turn the light on or off over on the other end. Now this is all pretty awesome, but can we do any better than this? Well, let me show another quick demo, and I need to open the here we go. So what you see here is we have a truck, and the truck has on its back a Raspberry Pi sitting. And the Raspberry Pi has on one of its USB ports has a wireless Wi-Fi card that allows it to connect to a WebSocket server. And the front, it has a phone wire to it, so we have the little video there. Okay, and let's pause for a second here. Here in this case, you can see the Raspberry Pi attached to the two trucks, but in this case we have two trucks, and we are going to see how the truck is controlled. Here in the front I have my phone, and as I am tapping on the phone, you see the wheels, the front wheels of the trucks moving. So the beauty of this world is that I am publishing the information, the control information, left, right, forward, backward, and anybody out there can listen to that, just like in good old messaging. In this case, we were using JMS. And so we have two of these trucks listening to the messages. So the two trucks are doing this synchronized swimming experience. They are driving nicely back and forth. Looks like one of them was charged a little better. Okay, so what was happening here? We had two clients, the truck, or I would say the Raspberry Pi sitting on the truck, and my phone, or the browser running on my phone. Both of them were connected to the same WebSocket server that was sitting out there somewhere in the cloud. This guy was publishing the control information, and the other guy was subscribing. This is actually a good example for WebSocket being language agnostic. Given that WebSocket is a wire protocol, it means that on the Raspberry Pi we had the Java client library running. Here on the phone we had the JavaScript client library, and it was absolutely agnostic. Message published. Message broker routed the message back, and the WebSocket server made sure that over the web it's delivered to the client. Okay, let's move on and take a look at a slightly different scenario. The scenario is that we have an airplane, and the airplane has a satellite connection. Through the satellite connection, the airplane can publish all of its telemetry data, and it lands somewhere on the globe. There is a message broker sitting somewhere in the architecture, and it allows us to take all these messages that came in through the satellite connection and publish it out to any subscriber. In this case, it could be a native application or a browser-based application. Wouldn't it be nice if we could build something like this? Well, we tried, but the problem was that we couldn't get an airplane, so we decided to get a quadcopter. And this is the quadcopter that is sitting here. This is a DJI Phantom 2 quadcopter. We wanted to get as close as possible to the real scenario, and also wanted to play around a little bit with it. And But then we had a satellite antenna or a satellite terminal that is about the size of a laptop. So this quadcopter can lift about 2 pounds, about 1 kilogram. The battery lasts for about 20-25 minutes, and another FAQ, the price is around 500 pounds. We bought it for $670 in the US. So we need to have the satellite connection to get as close as possible to this outlined scenario. But since the quadcopter cannot lift the satellite antenna, we had to come up with a workaround. And the workaround was that we mounted a Zigbee or created a Zigbee connection between the quadcopter and the laptop that was down on Earth. This is a long-range Wi-Fi connection, a peer-to-peer connection. And that way we could get the telemetry data to a laptop. And then from the laptop that happened to be running a Java application, could have been any other language, we connected through the satellite connection all the way to the other endpoint. So all of this on the left-hand side was running in California. And the satellite is operated by Inmarsat. That's a British company here. So when I connected from this laptop, I lost my mouse. When I connected the laptop on the left-hand side through the satellite connection, I got a British Telecom IP address. I went to google.com and then I ended up on google.co.uk. And then, as the messages were published from the laptop, they all arrived through the WebSocket server to the message broker, and then again through the WebSocket server, they got published out to the clients, anybody who was interested in that data feed. And I almost forgot to mention that we have a handful of sensors mounted on the quadcopter. We basically mounted it underneath the belly of the quadcopter. At our booth, you can check it all out. It had a GPS antenna, so it was an Arduino-based little system. A GPS antenna, had an accelerometer, a compass, humidity and temperature sensors. So all of this data was published out. This is the DJI Phantom 2. You can buy it with a gimbal that's underneath the quadcopter if you are into video. That was secondary for us, so we used a simple GoPro camera in the basket that was mounted underneath the quadcopter. For us, it was the data that was really important. So here we are sitting in our green room. For whatever reason, we have a room that's painted green in the office with this little box. It's like a food container that contains the stack of our sensors. And you can see there is a 9-volt battery that powers the whole thing. On the right-hand side, you see the GoPro camera. On the left-hand side, you see the stack of these sensors. Here, this is a different view. This is the GPS antenna that we decided to mount on the outside of this little box. And we use these little plastic cables to strap the box to the quadcopter. This is the satellite antenna that we rented. This is what the smallest Inmarsat satellite antenna looks like. And I was carrying happily around this antenna from place to place. Interestingly, it always had to face the same direction because the 11 satellites that Inmarsat has are geostationary satellites, so they always look to be at the same point. But as I was carrying the satellite around, after a day or two, I noticed that there is this little sign on it, that yellow sign that indicates that you don't want to be closer to it when it's turned on than 0.6 meters because your hand may be ready for lunch. There's some pretty serious microwave stuff going on. So after that, I was not carrying it that happily around anymore. Here you can see this is in San Jose, right behind our office. These are many of the engineers who are working on the product. And here, this is the first test flight when we were flying it around. So let's take a look at what it looks like when it flies. So first we take a look at the actual architecture. The quadcopter can fly up to 700, 800 meters. The Inmarsat satellite is at 35,000 kilometers. It's very high up. And I got the IP address from London, as I mentioned. The A to B latency was about 650 milliseconds. So to get to data to London from California, it was 650 milliseconds. And then we took all this data and we publish it out to the web. So anybody out there on the right-hand side, could be a mobile device, a tablet, a web browser, or a desktop application, can subscribe to that data. So from this point on, we are basically publishing a lot of data out there through this, the WebSocket communication channels, all the way to the clients. And we measured some pretty low latency endpoints that included the Norwegian weather station on Antarctica. It included Kazakhstan and Namibia. And what we concluded to was that the latency between A, B, and C, so between A and C through B, was under 1 second. So what this means is that you can have an airliner flying over the Indian Ocean, have it connected through a satellite connection that publishes telemetry data out there that can reach any web-connected client out there on the public internet. And when it makes a left turn, within a second, you would know about that anywhere out there in the world. So we figured that that's pretty impressive and sounds like quite a fun. So after the architecture, let's take a look at what it looks like when it flies. I still have the Kaazing sticker on the bottom. So here we have the quadcopter on the down landed, and you could see for a moment the box attached to the bottom, to the belly. On the bottom right, you can see the video recorded by the GoPro that was mounted on it. And then in the background, you see the map. Every now and then, the map is going to move a pixel or two, left or right, depending on the sensitivity of the GPS. In the middle, you see a compass. You see pitch and tilt status as well. On the left-hand side, you see speed. On the right-hand side, you see altitude. And in the bottom left here, you see the temperature sensor. So all of this data was nicely communicated down to the laptop through that Zigbee wireless connection, and then the laptop shared all this information through the Inmarsat network to London, where we had our WebSocket server running along with a message broker, and then any client could connect to the server from the web, and the overall latency was under 1 second. So this is what it looked like when it landed, and this is the kind of the selfie that we took with the quadcopter. Okay. So in conclusion, I included pretty much the same architecture diagram here in case you wanted to see that in the slides. So what we can say is this awesome web communication technology is not just for the web anymore. It is very straightforward and pretty easy to build connected devices. When you have these connected devices, then there is nothing that would stop you from connecting them to the web. And when you connect them, then you would probably want to use, if real-time and event-driven nature is important to you, you probably want to use WebSocket for this. Very important lesson is that WebSocket is a transfer layer protocol, or can be used as a transfer layer protocol. There's obviously nothing that would stop you from going against WebSocket directly. But WebSocket is very low level, so if you want to build something semi-serious, then using the right target protocol is important. What does Kaazing do in this whole story? Well, Kaazing has been around for about 5 years, and other than contributing the WebSocket, or a significant part of the WebSocket standard, Kaazing has this communication platform that is solving a number of very hard problems in this space. There are some very hard problems that ranges from lockdown firewalls to penetrating various network intermediaries, all the way to clients that do not support WebSocket natively. If you have an older Android phone, then it does not have native WebSockets clients. If you want to scale out to hundreds of thousands or millions of users or devices in this case, or you want to integrate your communication infrastructure to an existing enterprise security system, there are many, many challenges out there, and these are the problems that Kaazing is working on. So as a takeaway, I wanted to point you to a handful of pieces of information. We do have a tutorial on using PubSub on top of WebSocket with JMS on the tutorial.kaazing.com URL. We have more information about our telemetry experiment on kaazing.com/telemetry. And a couple of people from Kaazing have written and published a book on WebSocket that was the first book out there about WebSockets. In addition, we have a booth out there. You can easily recognize it from the orange. We also have an orange gem box that we are raffling off. If you are interested in it, then stop by, and that's something that you can enroll in. And this is my contact information. Well, thank you very much for your attention, and I'm happy to answer questions if you have any. Yes?
Does the WebSocket provide any kind of keep alive except for TCP/IP development? I'm asking because Amazon, for example, their load balancing kills any connection which is idle for more than 60 seconds.
Yeah. So does WebSocket provide any keep alive connection? Yes, WebSocket has a ping and pong as part of the protocol, but WebSocket has a number of other kinds of challenges, things like your connection breaks in the middle of communication. Maybe you are driving in a car and a train and you go into a tunnel. WebSocket does not provide any reconnect functionality. So if your connection breaks, then it's your problem. This is where the importance of higher level protocols comes into the picture. So if you are using one of these higher level protocols, then it can be handled there, and actually many of our customers are using that. We happen to have a customer that is a European train company that is using WebSocket with some iOS devices for communication between their engineers who are driving the trains and the data center, and they're basically giving hints to these drivers when to slow down or when to speed up, because apparently it costs a lot of money to stop a train, but if they have the prior information about a red light, then they can slow down and don't have to completely stop. Okay. If there are no more questions, thank you very much for your attention, and we have a booth out there. You can always stop by there. Thank you.